Hey folks, I had a question on number 29, and we are asked to find the inverse of this parabola, right? And if I was going to just draw this parabola, it would look something like that, which it's technically not one-to-one, but if we restrict its domain from -2 to infinity, so around here, and I didn't do it the world's greatest job with this, right? Pretend this is the vertex, then that would become a one-to-one function because it would pass the horizontal line test. So if I've got that restricted domain on this parabola, I can go ahead and find that inverse function. So anytime you want to find an inverse, start by making your function notation less fancy and just rewriting that as y, right? And then the next thing is always to interchange x and y. So what I mean by that is instead of y here, I'm going to write an x. And then you see there was an x here and here in my original function, and I'm going to rewrite it as y. All right, and then once we get there, our goal is always to solve for our new y, right? Because in the original function, you had y isolated, but now you don't. Y is over here. And I'm going to go ahead and just kind of erase all of my scratch marks at this point, or my highlight marks. And what you essentially have is if you want to solve for y, you can see you have a quadratic equation for y, right? So anytime we want to solve a quadratic equation, right, we have to set that equation to 0. And then either factor or use the quadratic formula. So I'm going to move this x over here, right, by subtracting x. And then I do have a quadratic equation with y. And where this gets funky and a little bit new for us, a is 1. And just so we're clear, that's because the lead coefficient here is 1, okay? Now b is 4, right, because the coefficient on my linear term is 4. But c is 1 minus x. And I think we're used to c being a number. This might be one of the first times you've seen one of your values of a, b, and c in the quadratic formula actually have a variable in it. But I'm going to use a, b, and c and plug that into my quadratic formula. So when I do that, right, I have negative b, which is -4, b squared minus 4 times a times c all over 2a. Right, so let's start PEMDASing. This 4 times 1 is 4, right? This 4 squared here, I should go in order. 4 squared is going to be 16. 4 times 1 is 4. So ultimately, right, if I kind of look at this, I have 16 minus 4 multiplied to 1 minus x. So I'm going to distribute that 4, right? So when I start to distribute that 4, I'm going to go ahead and say I had 16 minus 4 plus 4x. Right, and that's where you're seeing this in here. And I can combine like terms. So let's go ahead and simplify this. So I'm going to extend, actually let me move this up just a bit so we have some room. I'm going to extend this. So ultimately I have -4 plus or minus the square root. And if we look at this, I'm going to have 4x plus 12 all over 2. And the reason I say 4x plus 12 is because I have 16 here minus 4. And that radicand, the 4x plus 12, it has a GCF of 4. So I have -4 plus or minus the square root of 4 times x plus 3 all over 2. All right, but we know the square root of 4, that can pop out of the radical and become a 2, right? So I have that in there. All right, and then what I wind up doing is this 2 can divide into both of those terms on the numerator. So -4 over 2 is -2, and then 2 root x plus 3 over 2, the 2's cancel, and that's why you see there's no coefficient in front of that radical anymore. So I've simplified that radical, and that's all great, but we got to figure out which of these two functions is my inverse. So I have two candidates. I have y equaling -2 plus the square root of x plus 3, or was my inverse function -2 minus the square root of x plus 3? And what we really need to focus back on is the domain of the original function. Okay, so if the domain of my original function was -2 to infinity, that should be the range of the inverse. So I have to kind of question which of these two graphs, right? This one or this one? Which one had a range of -2 to infinity, right? And if we kind of think about how this graph would go, and when I say this graph, either this one or this one, we think about our toolkit function, and I'm just going to make a little, I'm going to go over here because I'm running out of space. Our toolkit function is square root x, right? And we know it looks like this essentially. All right, so then let's think about this. If I have a plus 3, which I do on both of these, that's going to shift my graph left 3. So if I think about the square root of x plus 3, right? Oops, let me give some space. 1, 2, 3. It looks something like that, yeah? Now, if I think about, let me go ahead and get my highlighter again. Let's switch this up. I've got minus 2 out here. That's going to shift my graph down 2 units, which is fine. And again, I'm running out of space, but if I think about y equaling negative 2 plus the square root of x plus 3, right, I'm going to go 1, 2, 3, down 2. It's going to be here and go something like that, right? And then if we think about the difference between these two, I'm going to highlight it. One has a plus, here has a minus. So if I think about that minus, right, if I want to adjust that graph, and let me just put it right here, where I'm going to go 1, 2, 3, down 2, and instead of going up, I'm going to get reflected, right? And so when we think about the ranges of these graphs, when I say these graphs, I mean this one versus this one, we want to think which one had a range that was negative 2 to infinity. Well, it's this one over here, right? It started at negative 2, and then it went all the way up. And I know I have a lot of chicken scratches on there, but if we take a look at that, this is going to be my inverse function. Now, if you had wanted to write it as the inverse function was negative 2 plus the square root of x plus 3, that's totally legit too. All right, thanks so much. Bye.